That's okay. So what do y'all want to go over? More Q equals MCAT stuff, or kind of do a little bit of a throwback for gases, or Q equals MCAT? All right. Let's work this one. Make sure your calculators are out. You're going to make them. Okay. So let's go ahead and start here. So the specific heat capacity of silver is 0.24 joules per gram degree Celsius, correct? All right, that doesn't give us a question, so let's keep reading. Calculate the energy required to raise the temperature of 150 grams of silver from 273 Kelvin to 298 Kelvin. All right, so that's what we're going to be working on right now. So what do we have here? We have you all agree that this is an initial temperature, yeah, because it's going from 273 and then to a final temperature, T final, right? So whenever we have our final and initial temperature, we have delta T. So in this case, delta T equals 298 minus 273. Do we agree? Yeah. So then that means delta T equals 25 Kelvin. A change of 25 Kelvin, right? So that's one component that we just figured out. But what's the basic chemical principle that we're going to have to use to solve this problem? What is maybe an equation that we are going to have to use? So we're asked for heat, calculate the energy, which yeah, Q equals MCAT, right? Because Q is a form of energy, is equal to MC delta T, right? And we knew that because when we were given specific heat capacity, so that's the variable C, so that should lead us to start thinking about, using this equation. Yeah, we're also given mass, so this is, yeah, and then we have delta T here that we can calculate. So therefore, we have all the information to calculate Q. So Q equals the mass of 150 grams times the specific heat of silver, which was 0.24 joules per gram degrees Celsius, and then the change in temperature, which was 25 Kelvin. If we put this into our calculator, we should get going an answer of 900 joules. Just about. Y'all check my work. Check if that's what y'all did.
Well, it's negative, like, it is not matter in
so you're talking about like the final answer we got here is a positive number. Is that what you're saying? Yeah, so I didn't write the positive sign, but it is a positive number, and it makes sense, right? Because if I'm the silver has to gain, denoted with a positive, gain 900 joules of energy to raise its temperature, right? If it was negative, it wouldn't make sense. And the negative and positive for this problem comes from this part here, the change in temperature. Because the change in temperature is positive, you're going to get a positive Q. But if it had been negative, meaning that the silver is losing heat or losing energy, that means you would have ended up with a negative value here. All right, does that make sense? Yeah. So sign does matter. Calculate the energy required to raise the temperature of 1 mole of silver by 1 degree Celsius. So how would we do this?
Well, in terms of find. Oh, since we're given on the previous question, we were given 150 grams. If you want to find 1 mole, we have to take that divided by milligrams.
That would give us however many moles are here,
Oh,
but not the 1 mole of silver. Where could we find the mass of 1 mole of silver? Periodic table, right? So this doesn't tell you that, but you have to realize, okay, mass for 1 mole of silver. What is the mass of 1 mole of silver? Because this is delta T, right? They didn't give us a final and initial. They just told us that it changes temperature by 1 degree. That's the definition of delta T, right? So therefore, what we can do here is if we find the mass of 1 mole of silver, which looking at a periodic table is 107.868. 107.86. And we already have the specific heat that was given at the very beginning. We can just find the heat here. So 107.868 grams times the specific heat of 0.24 joules per gram to Celsius, multiplied by the change in temperature of just 1 degree Celsius, which that doesn't do anything. This is equal to Q. The Q is equal to 25.89 joules. So what's interesting about the value that we just got is that because we specifically talked about the temperature or the heat required to raise 1 mole of substance by 1 degree Celsius, what is that the definition of? Not quite. So specific heat is the amount of energy to raise 1 gram of substance by 1 degree Celsius. So if we're talking about 1 mole of substance by 1 degree Celsius, we're actually talking about the molar heat capacity. So that's a term you might have learned in class when you went through all the different values or the variables for heat capacity. You have specific heat capacity, and the molar heat capacity, and then the heat capacity is a different one that you will use in different types of problems. All right. Let's see this one. This one's a little bit different. So it takes 1.25 kilojoules of energy to heat a sample of pure silver from 12 to 15.2 degrees Celsius. Calculate the mass of the sample of silver. So go ahead, try this problem. I'll give you all 3 minutes to work it out. Please talk to your neighbors. Start the timer for 3 minutes. Yeah, so talk to your neighbors. If you get stuck, try to help each other out. Okay? And then we'll go over it.
So in these equations, do you want us to keep it as Celsius, or you want to change it to Kelvin?
So remember, it doesn't matter because if it's change in temperature. So let me get this straight. If it's dealing with gases, it matters. Gases need to be in Kelvin. But if you're dealing with thermochemistry, and you're just talking about solely the change in temperature, a change of 1 degree in Kelvin is equal to a change of 1 degree in Celsius. So it doesn't matter.
And it's a solid iron, so it doesn't matter.
But
Because it's pure iron, so it doesn't matter.
Oh, we're getting art.
it doesn't matter that it's pure. It's all about the what's it called? How the numbers end up working, how the math ends up matching. I'm gonna have you can do 59. All right. Classical. So they can do a follow first. Well, this isn't the T final one.
Yeah, that's a civil oil. Yeah. And one CMT. One CMT.
Walk around. You have a question? Yeah.
The concentration in joules over moles times Celsius.
You mean the specific heat, right?
Yeah,
Yeah, joules. No, it's joules per gram of degree Celsius, not mole. That would be the molar heat. 15 seconds.
15.
Yeah, I don't do it this much, like as much this semester. Like last semester, I used to like use it.
Yeah. All right, ladies and gentlemen. All right, it takes 1.25 kilojoules of heat, of energy to heat a sample of pure silver from 12 to 15.2. Calculate the mass of the sample of silver. So we are given Q. Y'all agree this is Q?
yes.
Yeah, it's the heat or the energy required to do this, right? So it's the energy being transferred. And then we have our T initial, temperature initial, and then our final temperature. So what do we have here? Yeah, delta T, which is going to be 3.2 degrees Celsius.
Should we change 1.25 kilojoules to joules?
I should, exactly. Yeah, I was going to get there, but because our specific heat, which is 0.24 joules per gram degrees Celsius, because that's in joules, that means this needs to be in joules as well. So to get that, we do 1.25 kilojoules, and for every 1 kilojoule, there's 1,000 joules, and so we get 1,250. Now all we're doing is just solving for the mass using what equation? What equation relates change in temperature, specific heat, and energy to mass?
Q mass equals Q over specific heat times delta T.
Yeah, so that's one way to say it. So the Q equals MC delta T, right? Just rearranged for N to solve for N. So doing that, we'll get 1250 joules divided by 0.24 and then 3.2 degrees Celsius. So with that, we can go ahead and put it into our calculator, and we should get about 1627.6 grams per N. So how would that problem go? Pretty easy, right? There, just keep practicing though. Make sure you get really good at these so you can solve them even faster. So again, this is probably going to be one of the easier problems that you will have in a test. I think the problems that we went over on Monday were a lot towards the end of the class or end of the session on Monday were a lot more intense. All right. So Rich is going to do number 59, but I'll give you a couple minutes. Give you 2 minutes. See what you know. Write down relevant equations, maybe label the variables you're given. Try to solve it if you can. If you can't, don't worry. Right. Let's see it. Time is up.
All right, let's go over. So, 150-gram sample of metal at 75 degrees Celsius is added to 150 grams of water at 15 degrees Celsius. Temperature of the water rises to 18.3 degrees Celsius. Calculate the specific heat capacity of the metal, assuming that all heat lost by the metal is gained by the water. All right, let's just mark down everything we have so far. So 150-gram sample of metal. So this is mass of metal. Just gonna put M metal. 75 degrees Celsius. Is that a final temperature or an initial? Initial. So T I we'll put metal in here as well. Added to 150 gram, 150.0 grams water. So this is mass water at 15 degrees Celsius. Again, final or initial temperature? Initial. So T I H2O. What about this 18.3?
That's final.
That is indeed final. So this is T. Yeah, that's T final. So we're tasked here to calculate the specific heat capacity of the metal. So we want to find C of metal. That's what we want.
We do not heat capacity of water.
What is it?
1.1.
26?
Or is it 184? 184.
Yep, very, very close, but it's 4.184 for the units.
Joules divided by grams degrees Celsius.
Yep, joules per gram times degrees Celsius. So, a little thing about me, I don't know about you, but I hate putting long ass equations into the calculator. So what I like to do is let's break it up into smaller stuff. So I know this from every calorimetry problem I've ever done. And I know that it says right here, assuming that all the heat lost by the metal is gained by the water. So we can do this little expression right here. The Q of the water equals negative Q of the reaction. So let's solve for our Q water first. So our Q water is going to be our mass of water times the specific heat of water times the delta T of water. So if we put all those numbers in, that's 150 grams times 4.184 joules per gram times degrees Celsius. And then our delta T is our final temperature minus our initial temperature, which in this case is 18.3 minus T. All right. What do y'all get when you solve for the Q of the water? The 2075.08.
2071.08.
2071.08. So do this here. Yeah, 2071.08. Now this is the Q of the water. So what's my Q of reaction?
Negative 2007.
Yeah, so our Q of reaction is going to be negative 2071.08. So negative 2071.08. Now we're going to solve for our mass, or sorry, our specific heat. So that's again negative 150. Because we're solving for a negative Q of the reaction, right? So Q of the water is negative Q of the reaction. So 150 times our specific heat, which is what we're looking for. C of the water, not the water, sorry, C of the metal. And times our delta T, which in this case is going to be, let's see, 18.3 minus 75. So we do our business right here. This is going to be 18.3 minus 75. gives us 56.7. We're gonna multiply that to 150. So we're gonna get negative 2071.08 equals negative 8505 C method. And that's probably an extra negative sign right there. I'll need that. So if we divide both our sides here by 8,505, so negative 8505, to solve or isolate our C metal, we will get that the answer is 2071.08 divided by 8505 should get an answer of approximately 0.244 joules per gram times degrees Celsius. No. That's how you solve this using good old fashioned math.
We thought to put the negative sign on the 150 times delta T, and I still got the same answer. 150 times the delta T.
Oh, yeah. That negative sign I put by mistake because, yeah. I was counting the negative twice. That's what I was doing. Because this delta T will already give you a negative answer, is what you want anyway. Yeah. Remember that you can't have a negative specific heat capacity.
Yeah,
That's not possible.
that's another thing, like making sure your answer is reasonable. If you got an answer of a metal, so we know metals can absorb heat and lose heat relatively quick, like quicker than water, right? That means it should have a lower heat capacity than water, which is 4.14 joules per gram. So if you got something in the range of 500 joules per gram degree Celsius, you know, your calculation might have gotten messed up somewhere. Or if you got a negative number for your specific heat, or maybe a different problem that was asking for mass, if you got a negative number for mass, you know, something went wrong in your calculation, you probably missed a negative, right? So asking yourself, does this answer make sense? Is gonna get you, is gonna save you a lot of points on an exam. Potentially. Right. Any other questions? The next one's very similar, so.
A biology experiment requires the preparation of a water bath at 37 degrees Celsius. The temperature of the cold tap water is 42 degrees Celsius, and the temperature of the hot tap water is 55 degrees Celsius. The student starts with 90 grams of cold water, while mass of hot water must be added to reach 37 degrees Celsius. Similar stuff, different variables.
I'll take care of this one.
Let's do another 3 minutes, Jim. We did a small walk around last time, so I'm gonna do a big walk around, you know, Jameson and Boone.
50 seconds. Time's up.
No, really?
All right, how do y'all feel about this problem?
I mean, I got to change the temperature.
There you go. Hey, that's progress. We need to change the temperature. So I'm gonna ask you that in a little bit, all right? Okay, so a bio major wants to do an experiment, requires a water bath. So we are asked to find what mass of hot water must be added to the cold water to reach a final temperature of 37 degrees Celsius. We were given the T final, right? The T final for both waters is gonna be what?
37.
Yeah, so this is our T final for both situations. And the initial temperature of the cold water was 22 degrees Celsius. And then the initial temperature for the hot water was 55 degrees Celsius. So what we can do is calculate both the delta T and the delta T for the cold and the delta T for the hot water, right? Because we know we're probably going to need to use this information. So delta T of cold water is equal to
15 Celsius.
yeah, so 37 minus 22, which equals 15 degrees Celsius. And then we know that the delta T for the hot water equals, what is it?
It's
37
minus 5.
Yeah, 37 minus 55, which gives us negative 18 degrees Celsius. Right. And those numbers make sense because the hot water is going to decrease in temperature and the cold water is going to increase, so those signs should be the same, right? The signs should, go along with what is happening. And that's what happens. So similar to the last problem, we always use the idea for these calorimetry problems or mixing one thing with a different thing at different temperatures of finding, where they equilibrate at. We're going to use the idea that the heat lost by one is equal and opposite to the heat gained by the other, right? So we can denote that as the heat lost from the hot water is equal and opposite to the heat gained by the cold water. Do we agree on that idea? It's like if you take an ice cube and put it in some cup of water. Originally, that cup of water was at 25 degrees Celsius, and after the ice cube gets put in there, they're going to find a temperature that they both meet at, right? So maybe it's like, depending on how much ice you get, it's going to be below 25 degrees Celsius, but above 0 degrees Celsius with the ice, right?
So because the hot water loses heat energy and the cold water gains heat energy.
Yeah, so the hot water is losing the energy and it's going into the cold water, right? So that's where this idea comes from. And we know that this is just equal to negative M, and if we denote the hot water as Q1 and this one as Q2, it'll make our abbreviations a lot easier for the problem. So this would be M1 times C1, maybe just no more correct, C1, delta T1 equals M2 C2 delta T2. So the twos are just coming from, I didn't want to write out the mass of the cold water, the specific heat of the cold water and everything. So I'm just changing this from Q of the cold water to Q2. This one's Q1. So everything associated with this Q is going to be denoted with a 1, and this one's going to be denoted with 2. What do we know about the specific heats here?
4.184.
4.184, and it's found on both sides of the equation, which means to simplify this, we can cancel them out, right? Because we're dealing with water in both cases, so that's going to be 4.184 for both, so we can just cancel those out, and it simplifies the math a little bit more. Equals M2 delta T2. So this is delta T2, this is delta T2. All right. Now all we're doing is solving for the mass of hot water, right? So that's going to be M1. So solving for M1, we get M1 equals negative M2 delta T2 over delta T1. And when we put all the numbers in, we get 90 grams of cold water times the change in temperature of the cold water, which was 15 degrees Celsius, divided by the change in temperature of the hot water, which was negative 18 degrees Celsius. And we get a mass of the cold water, or the hot water, that we need of 75.0 grams. That is our answer. Coming from an experimental side, how would you get 75 grams of water? How are you going to select that?
Put it on the speaker and play it.
Weigh it?
Yeah.
Yeah, the density of water is 1 gram per milliliter, right? So we need 75 grams, we just need 75 mils. You can probably find some instrument that can allow you to get 75 milliliters of water without having to get a balance, zero out balance, add water, add water, add water. You know, you get 75 mils, it should be roughly the same.
How much water did you have at first? No.
That's a question for you, and don't share that with the class, okay? That's a knowledge that only very few people can know. All right, number 61 is the next one. All right, any questions on the problem before we move on?
That's 1 gram and 1 milliliter.
Yeah, that's the density of one. On 61. If there's any questions at any time, now is the best time to ask them. Because if you don't, the next problem you'll be lost. And says the propagation of air that happens here. We don't want any propagation of air, we want propagation of success. We go for a longer walk than race. Let's do a T final question.
We're doing my way first, and then you can show them the trick.
Writing that problem. Color. Look, y'all look done, so. We'll go over that question.
All right, let's do this. Sample of nickel seated at 99.8 degrees Celsius, when around to 100, okay. And placed in a coffee cup calorimeter containing 150 grams of water at 23.5 degrees Celsius. After the metal cools, the final temperature of the metal and water mixture was 25 degrees Celsius. If the specific heat capacity of nickel was 0.444 joules per gram times degree Celsius, while mass of nickel was originally heat. So what do we really solve? Like, what's the point?
Mass of nickel.
Mass of the nickel. So we're solving for mass and I. And let's do this the Gillen way this time around. So Q of the water, right, as we've been doing for like all of these problems today. Q of the water equals negative Q of the reaction. The stuff we've been doing like pretty much all day. So we have 100, or this is what? Mass of the water, so mass H2O, times the specific heat of water, CH2O, times the delta T of H2O equals negative the mass of the metal times the heat of the metal times the delta T of the metal. So this is just like, because the Q, right, is equal to MC delta T, so I just expanded it a little bit. And since we're solving for the mass of the metal here, so M metal, that's going to equal the MC delta T of water. This is all water, all over the, or negative that actually, negative MC delta T of the water times, oh, I put water twice, my bad. This should be metal. So specific heat of the metal. So C metal divided by delta T metal. All I did here was I isolated my equation for the mass of the metal, because that's what we're trying to solve. So let's plug in all our numbers. So mass of water, right, is 150. The specific heat is what again? 44184. What are the units though?
Joules over grams times Celsius.
Yep, joules of grams times degrees Celsius. And then what's my delta T of the water?
1.5
1.5.
delta T of water. Yeah, because you got 25 minus 23.
Are you sure?
Yeah, because the final temperature is 25 Celsius.
Are you sure you're sure?
The final temperature of the metal and water mixture is 25 Celsius.
No, I was messing with you. You're right. The point is, the point of that was trust your gut. So yeah, you got it right. 1.5 degrees Celsius. And then the C of the metal, right? 0.444. Not just sound like Jeff Davis on here. C of the metal, 0.444 joules per gram times degrees Celsius.
Don't forget there we go.
Yeah, the negative side, the catch. So the delta T was the delta T of the metal.
Negative 74.8.
Sorry,
Or I guess for you, it's negative 75.
Yeah, but we'll do negative 74.8. Let's go to all the decimals today. All right. Does this answer make sense before we put it in? Because we have a negative number on top and a negative number on the bottom. And our total mass would be positive, which is what we want. So if we solve out this monstrosity, let's see here. So 150 times 4.184 times 1.5, then so the bottom, or the bottom is negative 941, or sorry, the top is negative 941.4, and then 0.444 times negative 74.8, we get negative 33.2112. So now if we solve this out, the negatives cancel. So that's 941.4 over 33.2112. And you should get a mass of the metal being 28.35. What are the units here though? Grams. It is grams. 28.35 grams. All right. Any questions there? Sort of similar to what we've been doing, right? Except for instead of solving for the specific heat, this time we solve for mass. Now let's move to another scenario similar to this, where now we're solving for the final temperature of the metal and the water after no more heat is exchanged.
temperature be weird. No, he doesn't. For whatever reason.
Anyone have an answer? I'm pretty sure I'm thinking off track.
I think I'm going down a rabbit hole, but I see no way of ending.
You're on.
Oh,
Go to mathematically solve, because you know X, T final is the same, right? So X and X, so now you gotta mathematically solve for X. Basically all the X, so. Alright, come on. I like to see that. They're all involved, so you getting more where it is not right. It's just called 10. 10 times X minus Y. Here you have the difference. The answer and ask yourself, does it make sense that the final temperature is less than the temperature of water that was initially? Water. Right, because at 25, and if you put in the common, it should be at least 25, right? Yeah. So 1x plus 1x equals. Your math, One, got an answer?
Obviously, I'm not.
Go ahead and do that.
Hello, Rich. Rich, what do you get?
What did I get?
Yeah.
Same thing you got?
Okay. 2 versus 1. So, obviously.
Oh, you put negative. But this one would be negative. Yeah, the both side over here. is negative. Negative. You put something hot, 25 degrees water. You would expect some of that 25 degree water to increase temperature a little bit. It's not, especially by that much. Yeah. All right, so the whole point of this problem is because this is the problem that I came across when I took this class. And I was like, oh my God, all this math and distributing, multiplying negatives, you gotta do all this negatives. How much of y'all hate it? How many of y'all hate negatives now? Yeah, right? I know, I was just helping him back there and,
I got the answer.
and the whole problem was the negative sign was missing. Can y'all believe? All right. So the trick for this problem, and this is gonna be a very helpful trick. So this trick works when you have it only works when you have things that are being mixed and they start at different temperatures and you're asked about a final temperature. So let me go to question, I think it is. Yeah, so question 47 is talking about a 295 gram aluminum engine part, blah, blah, blah. What is the final temperature? This is not a problem that you could use the trick in because you're not mixing two things, okay? So you wouldn't be able to use the trick in this problem. So don't immediately, if it asks the final temperature, don't immediately think of this. Ask, does it get applied to this problem? So let's see the equation that you can do. So T final is equal to, and it's a long equation, but it's actually relatively easy to remember. N1, C1, T1, M2, C2, T2 over M1, C1 plus M2, C2. So it looks very daunting, but if you just remember MC plus MC over MC plus MC, and remember that the top has the temperatures in it and top begins with the T, so the T goes to the top, then it's a relatively easy equation to remember. M1, C1 T1 plus M2C2 T2 over M1C1 plus M2C2. So the only thing is you have to just assign which one's gonna be 1 and which one's gonna be 2, and you have to be consistent when you're multiplying those two together, okay? So I encourage you, you have a couple minutes before I think someone else, I don't think anyone comes here. So try to use this equation to solve that problem. And I promise it should give you the right answer. And if it doesn't, I don't know what to say.
Rich already checked it out.
Oh, yeah, yes. But see how long that method was, and you have to worry about negative signs and everything? Could you imagine if I just told you about this before? I feel like a bad person letting y'all suffer, but I had to let y'all suffer so that way I could pull you out of the trenches and bring you to the light.
Like if the change in energy for one is opposite of the other one, why is it plus?
Because if you mathematically, so the way this equation gets derived is when you do negative MC delta T equals positive MC delta T, and eventually all the negatives cancel out to give you obviously a positive. Yeah. So it works. That's your piece of equation.
If you come to look at us up here, I'll watch you.
I get told that I'm wearing a hollow top all the time. Everyone said I'm a clown, so I guess
You're more self-respecting. I think. What you, Rich? You gotta be dressed like this.
I haven't celebrated Halloween in like
Celebrate.
5 years.
it's going to be Oppenheimer actually,
Or that.
or Barbie.
Well, you need hair extension.
I got the hair covered in that.
I forgot about that.
Hello, I'm done. Right. Hold on, I'm done.
I was waiting for you to see 25.69 on your calculator. Right, so no more negatives. No more negatives for these kinds of problems. Like I was over there trying to help it. I was like, what did you do? All the numbers are right. But it turned out you forgot a negative at the very beginning. So the harder way to distribute it. Like, how would you do it the harder way? So it's just the more mathy way. This is just one equation, you memorize it. The other way is you do, yeah, so you get, this gives you one number, right? Every time times that one gives you a number, and you distribute that number into 180 and into T final. And then this side gives you a number here, distribute that number into this and that. And then you have to solve, you have to get all your variables on one side of the formula. Go on this side, and then you get the answer. So remember, it's really easy. It's M1C1. So like, it looks, there's a lot of stuff going on, but it's really not bad. If we just got rid of the T's, then it's just the same thing over the same thing. But the word top begins with the T, so that the temperature goes on top. So you have to add the T's for that, and boom, you solve all these. What is the final temperature? But again, only use this when it's mixing like a metal, or mixing the metal and water, or maybe it was like the cold water mixed with the hot water that we did earlier. Those are the types of problems that you can use. The ones that have a single component, you cannot use this equation for. But those are typically easier than the others.
So point being, only use these for the coffee cup stuff.
Yeah.
So for the bottoms, it might not work.
Kenny was telling me like that there's an Alex part where it's just none of y'all can solve it. Like,
Bro, that was
I mean, we can solve it, we just don't want to.
yeah, isn't that bad? Very easy. You'll get there with your compound X, camping trips, and then fucking problem.
You started the computer, you don't even know what it is. You just made me stress, I don't know, Then you made me go on to the other one, no sense of it.
Wait, who's your third?
Me. It's like. Medium hair. Really.
You want to find them,
Indian,
I guess,
like kind of around.
yeah.
That was.
oh.
So, you like you're sitting.
Man, I should really go for a hoagie right now. You should go get a hoagie. I should go get a hoagie. Oh, a hoagie. Don't know? They sell them at the shop. Go get a hoagie.
is it Ted? Ted side?
Tench side?
Ted side.